printed ground effect vehicle. Luke.
I'm Alex.
I'm Clayton.
Let's first look at our problem statement and some of the criteria that are going to drive our project in this semester and next semester. So obviously it has to be 3D printed. The exception is things like motors and propellers and batteries and things like that, which we'll get online and then combine with 3D printed parts to create the final project. So one of the biggest criteria is going to be that 20-minute minimum runtime. So you'll see later in the presentation that's going to drive a lot of our decisions in terms of the wing shape, battery size, and things like that. So make sure we can hit that 20-minute mark. There's a 70 miles an hour maximum speed. Then the maximum frontal dimension of 0.5 meter, which is going to be about the same size as our wingspan at this point. So a little background on ground effect vehicles and ground effect in general and how that works. So it uses a high pressure air under the wings to basically push against the ground. Conventional aircrafts have that same high pressure under the wings. And then ground effect vehicles basically amplify that with using that high pressure air under the wings and pushing against the ground to generate extra lift. So you can see here a simulation from one of the programs we'll talk about later. There's an exponential curve as you get closer to the ground. Theoretically, 0, we're going to keep increasing the lift to the coefficient of motion or drag ratio on the y-axis. So we want to be about less than a wingspan away from the ground to get the most out of the ground effect and utilize it, get the most lift we can out of it.
So that's meters.
Yeah. Then so yeah, increased roll stability is a big thing with ground effect vehicles. So if you think about a plane kind of flying and one of the wings dips lower, starts to bank in that turn, then it'll basically self-correct itself as that lower wing drops into ground effect in self-correcting. So we'll use that later design. So these 3 programs that we used are going to drive a lot of the decisions we make. The OpenDSP is the first one. See here on the right, one of the wireframe designs of the concept designs we used. And OpenDSP basically allows you to create an airplane concept design and change basically anything you want about it: the airfoil, the fuselage design, tail wing. And OpenDSP allows you to export that file as an STL. We could use that to send it through the Rosie wind tunnel and test the design based on the lift and drag, those values. The other big one was the XFLR5, which is basically a CFD program that we can import a wing design and change the airfoil and things like that to get any aerodynamic values when you launch. So lift, drag, moments on the wing, things like that. Yeah.
Okay. After some research, we ended up with 3 diverse designs that show some promise: the tandem, the long wing, and the inverse delta. With the tandem, that one showed with the highest lift, but the end plates had issues with the stability. The long wing was the simplest prototype, but with the long fuselage giving us room for electronics, but it didn't have great use of the ground effect. The inverse delta was a proven GEV design with a large tail wing and the ability to float. I'm going to kind of skim through the decision matrix with the key points highlighted. The inverse delta kind of did better in most sections, so that ended up being the one we chose. With the cost, the only standing out one was the tandem. We probably have extra flaps, so that's increased the cost, which is the same thing with the electronics, with these being the same. The complexity, again, the tandem was the worst one, with the inverse delta basically being as simple as the long wing. Lift to drag, the inverse delta actually did win, as this one had the highest lift, but horrible drag. This one had great lift, great low drag. And this one basically kind of had both. Landing capability, they're mostly the same. Same thing with stability. How we chose our weights: lift to drag being the most important, as if it had a bad lift to drag ratio, you either have a hard time flying or just not fly at all. Stability and complexity. Stability, we want it to be able to fly, so if it has bad stability, it's not going to fly very long, or it's going to be harder to fly. Complexity, simple might be better, right? You don't have to make it harder than it needs to be. And electronics and cost kind of in the same spot as other designs fit within our budget, so it wasn't a huge criteria.
If we look at the prototype or concept design that we chose, we can see that we got the wing shape here. It's an inverted delta wing shape that kind of has an anhedral angle as it kind of sweeps downwards, and then it has a forward sweep with the longest airfoil being towards the fuselage, and then getting shorter and shorter as it goes towards the tip. So we know we wanted a long airfoil, so we did a simulation here in the XLR5 I mentioned earlier. We chose the NACA 2408 airfoil for our second prototype that we'll work on next semester. It did perform the best in this simulation, but overall, the different speeds and the different heights from ground, it did perform the best overall. So we got an aspect ratio of about 1.68, which is about what we expect from ground effect vehicles from our research. It's a little lower than conventional aircraft, which are a little higher, but it's what we expect. So we know we wanted buoys. We know we want to take off from the water. So buoys would be an important thing to allow for flotation. I'll talk about later the fuselage being 3 points of contact with 2 buoys and then one more at the end of the fuselage. You can see here from this picture that buoys also act as an end plate, kind of trapping that high pressure air with the anhedral angle from the wings, kind of trapping the air in there, creating a higher pressure, utilizing the ground effect as much as possible. The fuselage design kind of follows a similar shape to the wings there. You see it kind of sweeps down and then builds back up until the tail wing, which I'll talk about next slide. The super important thing about the fuselage, and something we'll probably end up changing by next semester, is being sure it's able to hold all the electronics, like the batteries and motors and things like that. That'll definitely be something we probably will change next semester. Let's say during testing, the fuselage needs to be, it's going to be the main body of the airplane. It needs to be structurally strong in case we have crashes or things like that. Having a prototype design, that should also float, as I mentioned earlier. Grab the 3 points of contact with the back of the fuselage, and then those 2 buoys for flotation in the water. For tail wing design, we wanted a large surface area for the tail wing. Ground effect vehicles have been known to have these pitching moments when going in and out of ground effect, so we know we want to have a large tail wing in order to kind of counteract that. Another thing is the change in center of pressure. Kind of same thing when going in and out of ground effect. We wanted that big tail wing to kind of resist the basically moments that are going to be created by that. You can see our final design here, created in SolidWorks, with all the parts put together. And then some rosy wind tunnel results we've got. About 3.5 newtons of drag and 14 and a half newtons of lift.
Okay. So this first design had overall dimensions of about 500 millimeters and 300 millimeters of length. However, the print bed that we could print in had 250, 210, and 220 millimeter limit. So we had to break this up. The idea was we wanted to keep the wing as close to one piece as possible. So we cut it close to the fuselage, as well as this had to be cut anyways because it's already outside the dimensions. So we decided to cut it like around where there would be enough thickness for our chosen assembly method to still work. And just to make it easier in SolidWorks, we just cut along this plane. So that's why the fuselage is cut that way. And we also cut the tail wing just so like in printing it'd be okay, as it's a very compact shape. Okay, so our chosen assembly method was tongue and groove, which you can see kind of inserts and holes. We thought that this would be the simplest method from the ones we could think of, which would be maybe nuts and bolts and screws. As using nuts and bolts and screws, you'd have to have some sort of opening inside the wings or fuselage so you could tighten and fasten them. This might mess with the airfoil or anything like that, causing the induced drag. We just don't need. So tongue groove was chosen to be the simplest method, as well as the inserts and the holes have a very tight fit, with the printer having a tolerance of about 0.05 millimeters. There is about a 1 millimeter gap in the entire thing. So in case the tolerances go into the upper ends, they'd be basically touching. So it's supposed to be very tight fit and it can just kind of stay like that. We're also going to use glue though. This is strong. Okay, some issues with the first print. Our chosen method of inserts, originally we're gonna have a hole inside this, so we could connect the electronics and the wires we go through. However, with our old battery they had chosen, it apparently didn't fit in either one of these pieces. So we have to use a different method to assemble the two. One that involves basically being hollow. So we can move the battery wherever we want. We have a new battery, but it's still gonna be an issue with electronics. Also, the fuselage is hollow. So for this assembly method, the holes basically act as a single point. So there's nothing fighting that moment arm for the wings, right? So they basically can move and we don't want that. So we have to move the holes to be inserts and the holes will go to the wings. With the wings, basically can sacrifice a bit of hollowness, having that extra thickness so it can fight that moment arm. As well, the back of the wings with the printer rotation cause it to be very rough. So there's some increased drag that we just don't need. Might be a little, might be a lot, but we just don't need it. We can fix it. So we're gonna try to fix the print orientation, whether we have to remove the insert so we can print or just add some stabilizer or something. But we'll fix that. Also, with the back of the fuselage, the chosen insert was a circle. This was mostly just for testing what would work. However, the circle allows for one axis of rotation, so it can move, and we don't want that. So we're gonna fix that so it basically can't move.
All right, so going into next semester, so we did a lot of the airfoil design and optimization of that. So now we need to work on steering, electronics, and like putting the entire thing together, as well as some testing various functions of it. So starting with steering, we kind of have decided on two options. This one being the first one, we thought this would be easiest option, essentially. We created a mechanical stop here to limit or to save strength from servo when there's like excess pressure on this wing. If we go forward with the design, we will have to make that obviously a little bigger. It's pretty thin, but it's just a 3-bar linkage that servo arm moves the link, which moves the flap. And our next option, which I think we're leaning more closely to, which is a jack screw, and that's what like most modern day aircrafts use. This jack screw will essentially push the flap out, and then this hinge will cause it to rotate. This is also very simple. Originally, we didn't know if we wanted to go with it because we didn't know if we had space in the airfoil, and we thought it could be slow. But some considerations later, we decided it would be quick enough for our design, and we don't need to be like turning all that fast for our design. So into electronics, we have transmitter receiver, dual motors for light, and dual servos for the flaps, as well as an Arduino for like autonomous mode. Starting with the user control, this is like the Arduino will solely respond to user inputs. Anything we put or ask the transmitter to do, the Arduino will respond to. Autonomous mode essentially will keep the Arduino in ground effect, so we don't have any control over the speed of the vehicle because it'll be done. The Arduino will be making those decisions, and then we will still control the like turning of the vehicle. So transmitter receiver, we like to go with a radio transmitter receiver, largely because of the range. Got a range of like upwards of kilometers. It has, this one specifically has 4 control switches. We can use those to go in and out of autonomous mode, and 2 analog sticks for steering and thrust, as well as potentiometers, possibly used for like keeping a controlled speed, so we don't have to worry about changing that. So into the Arduino system control. So it utilizes we're planning to utilize a distance sensor to basically sense the distance from the ground, and then the distance sensor will relay that to the Arduino, which will then make a decision on whether to increase motor speed, resulting in higher lift, or decrease it, resulting in less lift, bringing it closer or further from the ground, to maintain our ground effect, because that is the point of the. So now into the motor and ESC. So we needed a motor that could operate at low amps and still produce our required thrust of around 400 grams. to keep the plane in a cruising flight. The motors we've chosen have a 1,600 gram capability for thrust, and the spec sheet, for the motors say exactly what ESCs, electronic speed controllers we need, and how many cells we need in our LiPo batteries. So these thrust values were calculated with the propeller here in mind. So this is a tubular propeller. They generate a bit more thrust, but also some more vibration and a little less control. We plan to move to a 3-blade propeller because 2-blade propellers are often larger. And as you can see, this one, which is the one that the motor spec sheet had referenced, is 6 inches, and we're only 2 inches off the ground when like about to take off. So obviously it's not gonna work because like an inch of the motor touching the ground. So we're planning to change to the 3-blade, which will resolve that issue and give us a bit more control over the vehicle. And then on to servo. So how we did like our servo calculations and is we did a study of the drag on the plane when the flap is up and when the flap is down, and that difference would be like the drag induced by the one flap, and then calculated a moment using the length of the flap, and that's like the torque that the servo will need to create if we use a 3-part linkage. We'll need to redo these calculations if we do the jack screw. And then on the power and size. So as I said before, we have two 3-cell LiPo batteries, 3,000 milliamp hours. So with a 20% discharge safety to keep our batteries in good condition, we need and 4.2 amps consumed by the motors at 200 grams of thrust or 400 grams of combined thrust. We will have a 34-minute runtime, and this is enough thrust to keep our plane flying, as previously stated, and it will be at 14.5 meters per second, around 30 miles an hour, and 14.5 newtons. And then, as you can see, the batteries fit into the plane nicely. As I said earlier, we have an issue with our plane is like cut around here, and so we want to fix that. But the battery should be able to fit side by side for like symmetrical reasons and like weight symmetry. And these will be our biggest components, so it's reasonable to think that we should be able to fit the rest of the components in, considering that we have a lot of room left in our plane. And just in overview, our next prototype, pretty much as soon as we come back from break, we're going to be doing buoyancy testing to make sure that our buoys are large enough. We're going to implement the 2408 airfoil, because currently it's not on the plane for our first prototype, but after optimizing that, we are going to reprint and use that one. And then flaps need to be tested to see like the sensitivity, how they react to the transmitter. Consider like slots to put the electronics in the fuselage. Possibly improve the shape of the fuselage, add waterproofing, and hollow wings for weight reduction. Thank you very much. Open the floor to questions.
How much do the batteries weigh?
Like I think a pound for both of them. Plane weighs a little under a pound.
Something like that.
Well, that one weighs more, but after we haul the wings, the estimate is it'll go down to a little under a pound. But
I think it too.
Yeah, I see what you mean about the trailing edge.
yeah,
That'll be one of the big things we look at next semester, is just making those weight reductions as much as possible. For
Yeah,
all the
you
wings and-
consider the orientation of the print, because there's a pretty rough surface here now. With the way that you
Yeah,
did it.
that was mentioned in the presentation. Just trying to fix that because it is very rough.
Yeah, like this one, I think it is pretty reasonable, because I think you printed it like up and down.
right.
Yeah.
Yeah.
Mhm. Yeah, we plan to change it.
I think that would help with the roughness one, but also.
Yeah, definitely.
Are you only flying this over water?
So typically, like commercial ones and most designs are flown over just water. We hope to be able to fly it over land and water, but we would either need to create a system where we can have wheels and buoys, or we would need to like take off over turf, essentially. So currently, plan to fly over water. We can fly from water like to a beachhead and fly over land, but
Yeah. Okay.
I'll throw in here. So for your propulsion system, it looked like in your electronics diagram, you had two motors, or you're
Yeah.
using one or two?
we're using two. So
Where are those gonna be placed?
yeah. They're gonna be placed like, we're between two options, but currently here and here, they're gonna be placed and like offset just below the wing a bit. And, or, if we have issues with waterproofing with it below the wing, then they're like, we can make it relatively like splash resistant if you put it above the wings, but on the two, like sides of the wing.
You know how much your motors weigh?
They're light. I'm not sure the exact weight, but they're not, it's not like too significant.
And this, I mean, this is true for the other airplane team as well. Like the team last year really battled with weight,
Mhm.
so don't undersell the difficulty of
Yeah,
getting that from.
yeah, we're debating switching to airfield, like you mentioned your previous designs you did.
Yeah.
And yeah, but we're hoping that the like extra lift generated from the ground effect can help us, like the weight won't be as much of an issue as the other last year.
While we're on this slide, what like velocity was this run at?
14.5 meters per second.
Is that like what you anticipate your cruising speed?
Yeah.
Okay. All right, how are you gonna adhere the wing elements together? You've mentioned a glue of some kind.
Yeah.
Do you just like get some Elmer's, pop it in there, or what?
Yeah, we have a waterproof glue that's just super glue, and we will just like after we have it all together with the slots and stuff, and we've decided like we're done moving electronics in and out. We'll then glue it together with super glue.
Okay.
We'll have to have some way to pull like a slot to pull the wire out for the battery so we can charge it. But
You're gonna 3D print your propeller? Or are you gonna buy that?
buy it.
You had,
Oh, sorry, no.
you had some initial designs that you put up there. There was kind of three of them. They're all like pretty vastly different.
Yeah.
I'm just wondering if those came from inspiration from like somewhere else, other people that have done ground effect, or like how you guys kind of came up with these.
Yeah.
Yeah, we all kind of just created our own design. The tandem wing there and the inverse delta wing are the kind of two big ones that you see a lot of ground effect vehicles. And then the middle one there is kind of just we wanted kind of the most simple design and some way we could easily change variables and kind of see how that would affect the plane. So that's how that chose those planes.
Like used by the Russians in like World War II, and but like they stopped using it because of stability issues, and like took a couple nosedives into the water, and they're like, all right, we're done with that. And then this one is like the modern case is somewhat similar to the reverse delta wing. Is what people are doing right now.
Have you put any additional thought into how you're gonna replace sections of it quickly? Again, the team last year were replacing parts exceedingly frequently. Like, especially with the motors not being part of the fuselage, their wings were the first to go, like every time. You might, I guess I'm more putting a warning out there. You might think about how you're gonna handle that, especially with your important parts hanging off on parts that are probably gonna break first.
Right. Good.
And these are hollow? Is there like a truss on the inside?
No, we're gonna make a with the truss.
Like it like 20% infill or something? If you wanted a really strong joint bond, you could consider solvent welding. Like just put a little bit of acetone on there, put it in there.
Yeah.
It's actually a really good way to spawn 3D printed material together. It's better than glue, which is just an adhesive thing
Yeah, makes sense.
for consideration. Okay, I'm good.
All right, so I'll have a few comments, mainly echoing the weight thing is gonna be big.
Mhm.
Few notes on that. I think your airfoil, you've gone with the NACA series. Have you considered any really hot, super high lift cases? Looking at different airfoils? If you're not going that fast, it's a very low Reynolds number vehicle, and you're gonna need as much lift as possible.
Mhm.
Did you look at any other ones that were really designed for either this type of application or extremely slow flight?
Yeah, so we did look at the Appler airfoils, but it was a lot of Mac airfoils, kind of just throw them in the simulation and see what kind of drag or safety values we would get. But that was kind of overall the best one we found. We were kind of limited based on the concept design that we chose, kind of wanting that long airfoil and then kind of keeping that same shape. So that was kind of limiting the option being that too.
And the NACA did perform well, like out of ground effect too, and like inevitably, like we're gonna have to go out of ground effect to like go over objects. So it was,
Yeah, the main reason I mentioned that is it looks like your total airfoil does curve down. There's a lot of existing airfoils that already include quite a bit of curvature in them.
Mhm.
So that might be something that could help, dare I say, even cushion more on the ground effect. So it's a possibility.
Yeah.
Otherwise, you mentioned flaps. Do you really need flaps for this, or is that something that you're adding for control, or what was the motivation with flaps?
yeah, I guess for stability control.
Okay. Because I was thinking about it, if you have flaps, those could be used partly to help you set a speed and have some speed control over things, and then let that adjust your lift and use that as your control mechanism, so you still maintain control of the speed, but you can still maintain lift if that was the case. So rather than just let the controller fix a speed, I think that could be done with the controller control the flaps, you control the speed. Might be a better way to go about kind of orienting that control system. And the other thing to think about is in terms of turning, you're gonna need to have that rudder. Currently, the design is probably a little thin for that. I mean, yeah, you're gonna have some, in theory, vector thrust, but that's probably not gonna be as much as you think it might be. You may wanna consider how you're gonna get some sort of control laterally, and then also consider any of the roll effects that's gonna generate, because right now it's gonna be above the kind of main body, and that's gonna cause it to kind of tip one way, and that could be an issue for your ground effect.
Okay.
Yeah, so that would be the other thing to consider, just some of the controls and the wiring, all of that stuff is always a big issue in these small aircraft. The additional thing I will note is those vehicles, or your battery to your controller, you're also gonna need speed controllers.
Yeah.
And that is gonna take up a lot more space than I think you thinking. Those are not exactly small or small things, so just be aware, space utilization is gonna be a challenge.
Okay, I think we gotta move on to the next group. Thanks, guys.
Thank you.
Yeah, it's good luck.
Have to. I hate when people talk. I'm like, it's a must. Okay. Next talk of the session, 3D printed submarine. 20 minutes for the talk. Thank you. Now, go ahead.
All right, so for our project, we had the 3D printed submarine. I'm Sebastian Stadler.
I'm Jonah Hanker.
I'm TJ Cooper. For our problem statement, the main thing we were tasked with for delivering for the 3D submarine was it needed to be a remote control submarine. It had to be maneuverable. It needed to have a maximum frontal dimension, whether it's width or height of 0.3 meters. It needed to have a maximum traveling speed of 1.5 meters per second and a runtime of 20 minutes. And all the electronics, motors and batteries all had to be sourced commercially.
So to get our project going, we took 3 initial designs, the first being a traditional, which is like a typical submarine that you see every day. The next is a bullet shape or projectile, and then we took a combo version, which is a mixture of the aft and the bows tapering towards the center of the body. In these 3 designs, we were focusing on essentially 2 to 3 things, and that being we want to reduce the amount of drag that we have, make sure we had center buoyancy, and then fitting our components, our electrical components inside the center of the hull. With that, we took our initial 3 designs and used the Rosie wind tunnel simulations. And we took those values that it spat out and used a Reynolds and coefficient of lift relations to take our air results and make them water. So from this, we found that the bullet was our best design, being reducing drag and for the buoyancy reasons. With it being tapered at the front and going towards the center of the hull, we know that our weight is going to be shifted towards the center of the hull, making our buoyancy really good.
So for the center hull components, we have 2 main types. We have the through type, which you see on the left there. That's just a straight hole through. It has a keyed slot because inside of here will be the internal cylinder where all the electronics are stored. And so we want to keep that cylinder always angled upright. And then on the right, you'll see we have the ballast type. And so this X-ray shows that there's a cavity inside with a hole to the outside to fill with water for extra weight so we can lower our buoyancy and get closer because our 3D printed materials are very low in density. So we have to get as much ballast as we can. And as you'll see on the bottom here, we have to print it in 2 pieces with a specialized gasket in the middle that we also print out of TPU. And so those are held together, which we'll get to. And they're printed in 2 pieces because otherwise we'd have a cavity in the center printed axially that has supports that we couldn't easily remove. So we went with this method. In terms of coupling methods, we had 3 main ones. Magnets was the first one we went through with because it was very easy. We had a slight issue at the beginning because it had a slip plane because it wasn't really inset. So it was very easy for any shear force or moment to bring them apart. So what we did was we ended up insetting them to get rid of that. But we had a slight worry that constantly moving the internal cylinder with the electronics in it relative to these magnets might cause some sort of issue. And it honestly didn't provide much comfort above the last method, which we'll get to. The coupling clips is this method right here. You'll see that this is them apart, this is them together. Essentially, there's 8 on the circumference of the hull. It connects the 2 with screws. But the issue with this is they're highly reusable, but very tedious to work with. I mean, 8 on every single conjunction. We were getting in the realm of 128 screws to undo or redo every time you wanted to change the hull. So what we went with was the coupling rods. They're very simple and effective, but they are length dependent. It's just 8 rods that run through the circumference of the hull, and they're attached at the bow and the tail. I can grab the models in a second to pass around. And so those are capped at the ends, and that force holds all the pieces together with these gaskets in between each part to keep it waterproof. The one issue with length dependence is that if we change the amount of components we have, we need to get different rods, but getting rods that are an inch or 2 longer is a lot easier than reprinting 64 of these clips.
So the next thing we need to do was control a submarine. We went through multiple proposed ideas. One, oddly enough, was putting a bunch of pumps around the entire body of the submarine to push it left, right, up, down. We realized that was just not good for the fact of power consumption and weight. So we just went with a simple rudder design on the back of the aft. Within these rudders, we looked for certain characteristics, and that being at a neutral attack of, we want to minimize the amount of drag and have no lift. And then the next point was a 45-degree drag or 45-degree angle of attack because we want to maximize our lift and reduce our amount of drag in that point and the reason why 45 degrees was chosen was because any point after that basically treats it as a flat and it's going to slow our submarine down and effectively not turn it anymore. So from that, we took, I went on airfoil database and I looked through a bunch of airfoils and looked at their coefficients of drag to lift. To find these out of those, I found these 3 symmetrical airfoils that had these properties best suited for that. And I then took the profiles and made CAD components to put into the Rosie wind tunnel simulations. And outputted their parameters. These results are air results, they're not water results, because we know that in water, it's just gonna increase these results. So we were able to look at them face value. Alternatively, we used a decision matrix to enforce our reasoning of going with a certain airfoil, that being the first one that you saw on the last slide, the LWK 79100. With that, we got the best ratio from lift and drag at our maximum angle of 45 degrees. And when it was at its neutral point of no drag and no lift. The next thing with our rudders is the configuration of them. So we had two configurations, a cross and a plus, but we easily limited to the plus configuration because of two things, that being our control system. So simplifying our control system and the amount of components that we need for it. So within our cross configuration, we'd need 4 servos, and all the rudders would have to work in work simultaneously. And then that just became a lot more complex than what we needed for the scope of the project. With the plus, we could couple our rudders and use only 2 servos. So we could choose go up and down and left and right with only 2 servos.
Next thing we looked at with our submarine was the propeller design. The two main propeller designs that are currently out there are fixed pitch propellers, which is basically the head cap is fixed to the propeller, so it's one solid piece. And then the next one is the controllable pitch propeller, where it is a flat head, but inside of the propeller, it has a hydraulic mechanism that allows you to change the pitch of the propeller, so that way you have more control over your speed and other factors. However, due to not really wanting to design the inside of a propeller because of how complex it could get with the hydraulics and the mechanisms, we decided that we were just going to stick with the fixed pitch propeller. And because of that, we ended up coming up with 3 ideas that we wanted to look into to see if they could be beneficial to our design. Those being a vortex dissipator, twin propeller, and toroidal propeller. The first one we looked at was the twin propellers, which are usually meant for large sea vessels, which tends to mean that they have greater power and have increased speed, but at the cost of a higher fuel consumption. Because the 2 blades act in different angles of attack, it causes less cavitation on the blades. However, because there are 2 blades, it increases the weight, and it also causes a higher rate of corrosion on the blades, requiring more maintenance to be done. On top of that, it also is a little bit of a complex design. The next one we looked at was a vortex dissipator. Basically, that takes the vortices that are created from the head cap of the propeller and spreads them out to create a more propulsion from just the random bubbles that are generated. The vortex dissipator tends to be more of a spiral design that sits further up on the propeller. It also tends to increase the efficiency of the blade because it uses all the vortices that are created and returns them into propulsion, while also allowing for a reduction of noise generation. However, noise generation doesn't really have an effect for our design because that is usually mainly for military purposes because of sonar and such. The next one we looked into was the toroidal propeller, which is a ring-shaped propeller, which is a closed loop, and it kind of folds in on itself. It has comparable thrust to standard propellers. However, it doesn't require the additional weight that the other propellers have, as well as the material that is inside of the blade to produce that much thrust. It also tends to have an increased efficiency, and it also reduces the noise generation. So we took all these concepts together and threw them into our decision matrix, and we kind of just mixed and matched to see what kind of designs we could come up with. We had a standard propeller with a standard head cap, a standard propeller with a vortex dissipator, a toroidal propeller with a standard head cap, a toroidal with a vortex, a twin prop with a standard, and a twin prop with a vortex dissipator, where the main things that we were trying to get out of the propeller was low risk of cavitation, high efficiency, and a low complexity. While we also threw on there the things that were a little bit lower value to us, but we still thought of was noise, the time to produce, and whether or not it generally looked cool. From this, we got that the best concept that we had was the toroidal propeller with the vortex dissipator, and the worst was the twin propeller with the standard cap. After seeing that the toroidal propeller with the vortex dissipator was our best design, we looked into it and found that, at least from the research that we had, that it had not been done. But then again, most submarines are very about their propellers because of noise and the military aspect of it. So they don't really talk too much about them. This was the initial propeller concept that we wanted to go to, where it had the closed ring loop and the vortex dissipator on top.
So the next thing was actually controlling the submarine. We had two methods. Once again, it was acoustics and radio control. So acoustics would have been really cool, but the math is really, really complex. And also they're commercially, all their components are super expensive. So for cost reasons, we completely eliminated this design or this part to do. The next was radio control. So there's the usual 2.4 gigahertz radio control, which would be awesome for a submarine, and the fact of data and length, like how far we could control it. But there's one limiting factor, that is it can't make it through water. So to get around this, we had a proposed idea of a buoy that we could put the receiver and battery on it and have a tether going to our submarine, and then be able to control our submarine and get system data from it with that. Obviously with the buoy concept, we do run into the fact of like it could drag or slow our submarine down and cause surface drag if there's waves and stuff like that. But we didn't really go into that scope because the other form of radio control we could do is just lower frequencies that do penetrate the water. The only thing that we don't get from them is the system data. So it is possible to do that. It's just finding those components are actually a little bit harder to do versus 2.4 gigahertz that are more commercially available.
So for actuating methods, for the parts that are actually going to be along with the internal cylinder, those are going to have internal gearing. So that would be the main ballast and the forward dive planes. But the ones that are further away, that being the aft set, so the aft dive planes and the rudder, are going to be controlled with these through rods that go through the hull. And so these are going to be attached to servos. And so when it turns this little rod here, it in turn turns the rudder or the dive planes. So for ballasting, we have three main kinds of ballast: permanent ballast, variable ballast, and trim ballast. So permanent ballast is just to give us permanent weight, especially with these 3D printed materials. The density is low compared to metal submarines that only have to use this small amount of ballast. And so we're going to have this section labeled 2 here. This is a cross section of the internal cylinder. That section labeled 2 is reserved just for permanent ballast. That might be concrete, that might be metal weights, whatever we need to get to that low level of buoyancy. Variable ballast is what we control during operation. It's normally called main ballast. On a normal military submarine, that's the parts labeled 1. We forewent the ones on the end just for the one in the center for simplicity. And also that leads into trim tanks. We have the trim tanks on the fore and aft. Those are the ballast sections we talked about. Those will be adjusted manually to account for balance and add extra ballast. For the variable ballast, though, we invented this novel concept of the worm piston ballast, which essentially has this threaded rod in the center that when you turn it, these 2 piston heads on the end either come in or go out at the same time to either expel an even or take in an even amount of water to change our buoyancy to neutral. So for motor control and power, we're obviously going with the electric motor to begin, but in case we run into any issues with that, we do have 2 backups. First is a CO2 motor. The operating principle of that is down here. Those are very common on model airplanes. And so the way it works is essentially this. We have a CO2 cartridge that just provides high pressure and it runs this. There was a slight worry that the pressure might not be enough to overcome the pressure of the water, but we can get these in high enough pressure that low depth water is not any issue at all. They're very easy to control, but they take a lot of reloading. We need to constantly put new cartridges in just to save on electricity. And then the Stirling engine. I own a company in submarines and we use this concept for air independent propulsion. That chemical formula is for sodium acetate. And so it's the same principle as reusable hand motors. And so basically you put it into the supersaturated state, and then when you need it, when it recrystallizes, it lets out an exothermic reaction, which you hook up to the bottom of the Stirling engine, the top being the surrounding water for a low temperature heat sink, and you just generate all of that power from here. There was a slight worry that that would get too hot for the materials, but that only gets to about 65 degrees C, which isn't enough to cause any significant warping. But we're foregoing this for now, where it's just there in case the electric motor doesn't work.
Next, we wanted to look at the material selection because obviously it is a 3D printed submarine. So we went ahead and we looked at some basic materials, PLA, PLACF, PLA metal, PETG, PETG HF, and ABS/ASA. And we went through and collected the basic mechanical properties from them.
So of those ones, we discussed them and brought it down to a final 3 candidates, PLA, PLACF, and PETG. But we did have one slight novel issue with our application, is the extended exposure to water. And so we conducted an experiment to see if that affects the materials in any way. Our main worry was expansion or contraction of the hull that might cause breaking. And so we had 12 total samples, 4 of each, 2 dry, and then there was an axial sample of each and a flat sample of each. And we soaked each of them for 4 weeks, and then we put them in the tensile tester. And what we found was generally the soaking weakened all of the filaments, and there wasn't any significant expansion or contraction in either the axial plane or the flat plane. What we did find was the PLA, the layer adhesion was lowered and it experienced brittle failure, which we didn't really like. And then with the PLACF, it was interesting because soaking it actually changed its failure mode from brittle to ductile. So if you'll see here, this one looks about normal, but this one has these white stretch marks from when it started. It has this second set of data because it started stretching, whereas these ones didn't stretch much at all. PETG went about as we expected it to. It's known as water resistant filament. And so you'll see that both of these have those white stretch marks. They didn't very much behave differently. It's just the PETG was slightly less strong. And then this is our final prototype design for now. You'll see it has these 2 main through sections, and then this is the buoy for the radio receiver. It has these 2 trim tanks on the sides for adjusting our balance. It has the bullet-shaped bow and a parabolic tail. Inside, it has the worm piston ballast, and it has the coupling rods, like we mentioned. We have the plus configuration here and the toroidal propeller there.
Looking at the future development of our project in second semester, the main part of second semester that we're going to be starting to do is getting the initial components for our first prototype, as well as building our first prototype, and then just going through and just running as many tests as we can on it to see what we like, what we don't like, and what we can improve. And then once we start our testing by hopefully mid-February, beginning of March, we plan on just going from there until week 16 to continuous testing and improvement stage for it. From there, after we're done with the first sets of tests, we plan on going through and doing an interior and exterior improvement / redesign if there's any issues that we see, or if servos need to be thrown out to balance more. And then we plan on making the second prototype, running through and going that again, all those tests to make sure it runs how we want to and see what we want to change, what we like and what we don't like, until we get to hopefully print getting the final print made 2 weeks before the final presentation.
Okay. Yeah, I'll grab the parts we can pass around. I have a few for reference. I'll start here. Just a few.
Hang on here.
Those are still.
Everything's scaled down except for the.
Yeah, these are half scale to save on material. They are printed out of PLA because it's what we had on hand. These are not final.
Another reason why it has to be like so large is because doing like even the battery packs and everything on the inside, you're essentially limited by your inner diameter, not your outer diameter.
And also our inner cylinder only runs through the through parts, so it's not even limited.
Okay, thank you. All right. Q and or A.
Tell us more about how you're gonna prevent it from listing or just rotating around and getting finding yourself upside down.
In terms of ballast, well, you mean ballast, not ballast. So that's something that the planes and rudders help with. If you go here, go back to the final. These first of all help, but also the board set of dive planes. That's the reason that a lot of submarines have, sometimes they call it a sail or a bridge fin. We forewent that because that's normally for storing periscopes, masts and stuff on military submarines. There is a chance that there will be a slight listing, but due to the size of the planes and rudder, it's hard to explain without a lot of industry experience. Normally, the rudder and planes are very small in comparison to the size of the ship. These look small when you think about it, but these are actually relatively large compared to normal submarines. So the effect that they have on that moment and just turning the submarine is greater than it normally would be. If that answers.
Do you have more permanent ballast like at the bottom than you do at the top?
Yes.
So will that help?
Yeah, that'll help too. That's another thing. If you go back to the ballasting slide, that's why the main ballast is down here, because that keeps that way at the bottom.
That's,
Yeah. So where's your power coming from, by the way? You mentioned fuel consumption at one point.
It's battery.
It's a battery.
Yeah, okay, all right. So, yeah.
We just talked about other alternatives that if
Yeah.
electricity didn't.
Yeah, okay.
So fuel consumption was more of like a large scale, like this is what the propeller's pros and cons are.
Okay, all right. And then, so you have battery. Battery is probably gonna be quite heavy too. Yeah, so that ends up being permanent ballast. Is that like accounted for in the inside here?
Yes, so at the moment, what we have, if you go to the permanent one again, so we don't have a final, like this is our first prototype. What we have at the moment is an equation that gives us the buoyant force on this as a function of how many of each one we have is. So we know, I don't have the number on hand. We know what the buoyancy of this is and what the weight we'll need is. We just are going to find experimentally, it's not going down when we fill all the ballast. So we'll add some permanent ballast, and we do that extensively with these. These are just controlled by hand experiment.
Do you have a target depth in mind?
Not
We
specifically.
are limited though with our controls, so depending on like what form of control we go with, it would be limited by the fact of our tether length. If we choose a 2.4 gigabit controller, or if we can get a low range one, then obviously we can only go so far without it, like the frequency not reaching. Ideally, it would probably be like 5 to 10 feet, like I would assume we would do a lot of our testing in a swimming pool or something like that that's controlled, so like you don't want to hit the floor, so 5 feet would be my guess. Yeah.
Okay. Do you have a way to quickly change the ballast as you maneuver?
That would be we can't quickly change these, but that variable ballast inside will be able to quickly change. Basically, the point with that is just to change us from positive to neutral. And so it's just going to depend on how close we are to that threshold with the amount of ballast we do put inside.
And last one for me is you've got kind of this like push rod connections between the individual sections. Are those like press fit in?
Yes, if you saw on the tail and nose, I'm gonna grab.
Yeah, I saw them, but
So these, if you look through them, they have a slightly smaller diameter portion inside. And so they are press fit through the ends using screws. So there's a threaded end to the rods and you put the screws in, and they're press fit together. I have a 3D printer that I 3D print TPU gaskets on. So every point is gonna be gasketed.
Okay, that's enough.
So I was gonna ask you a little about your control systems. Have you considered what you're using for all of your, dare I say, rudder, other parts of that? And is that gonna be waterproof?
Like electronics?
Yeah.
If you're talking
Button slides.
Yeah. So we did look at servos. I found a waterproof servo that was up to 20 kilograms. So we would be plenty of torque for us to use, and we could then not really have to worry about that. So we overspec that. I did original calculations with the rudders where I just took the length and then we calculated the torque of what we need. It was around like 5 to 10, depending on what we chose. So we just doubled it to be extra safe in case there's like water turbulence or anything that way that we were meant to.
But do you have a way of waterproofing that?
Yeah.
The internal cylinder, you mean?
Well, so anywhere you're gonna have your control system, that's gonna have to go through the hull at some point.
Yes, so the internal cylinder will be self insulated from the water, and it will also like I mentioned, the control rods. Those will be gasketed outlets that will be especially waterproof to make sure nothing gets inside, and then also the entire shaft at the edges, especially in stuff like the propeller. Those are all going to be gasketed and waterproofed specifically to make sure, but the internal cylinder specifically is going to be very much waterproof.
For the rotors on the Atlas servos would be inside of our main hull, and then we'd have rods to control them far from the distance.
Do you have an estimate of your total size / weights of everything at this?
So diameter, outer diameter 6 inches, inner diameter 4 inches. If you go to the final design, 612. So this is about say 5 feet. Those 5, 6. Is what we have 4. It might be 4. I mean, this is I'm doing this in my head on the fly. I didn't think to have a number because this is 6 inches. This is 6 inches. These two are 3, and then these two are about a foot apiece. So yeah, around there.
We also have the ability to, like, the reason why we went with the variable hull is so on, we could change that. That being if the weight is too much, we can just add parts that are air bound, so we'll reduce our weight versus add where we have places in the hull that are water filled. So we have a very good idea of control for that in the future when we truly get into the depth of it. But we're more worried about the actual structure and making sure the components wise is good.
And also with that, for these through sections, we have 2 versions of each, one that's 6 inches, one that's 3 inches. These are 3-inch ballast. If that's not enough, we'll swap it to a 6-inch ballast on each side for more ballast.
Right. Did you do any preliminary calculations for what size ballast you needed?
Not specifically because we also need to account for the weight of all of our components. We didn't have a specific weight when we did all of those, so we don't have a specific relation for that. We were just going to go with it on the fly and adjust it with that permanent ballast. That's why we left so much space for permanent ballast, was so that we wouldn't have to worry as much when we were constantly changing this whole, how long it's going to be, what components we use and all that.
Can you go back the slide with you said, is that a worm? So you're using a worm gear or?
So I call it worm gear because this whole shaft here is threaded. So this is going to be a gear that's connected up onto the control surface. It's omitted on this figure, but there will be a gear here from the servo, and that'll turn this, and that turns this long shaft that's threaded all the way through, like on a 3D printer, the vertical ones. And each of these pistons is oppositely threaded, so that they move in or out.
And
It's watertight.
Yes, these are all gasketed too. It doesn't technically have to be, but it will be.
did you do the calculations on what you'd need for the torque on that? Because of the compression of the air within that inside, like the center part?
I didn't adjust for that too much. I did know that the pressure in here is gonna be higher. That's why, what we said in the report was this is probably gonna be metal. And I assume that these parts might be too. I didn't think about if the servo has to be stronger. We can figure that out. We didn't do a specific calculation on how high the pressure gets in here relative to how far they in, because I didn't imagine it would be much of a problem. But if it does end up being a problem, we will account for that.
Yeah, I mean, like the visual suggests you're gonna have a problem, right?
Well, this is not necessarily to scale. This is not necessarily to scale. This is just to show the working principle.
Right.
Okay, got one of that true. Thank you.
I'll be right back.
No problem. Last one of the day, take us home. Take us to Christmas. Sorry, holidays. Sorry. Don't buy some fires. I got most of my comments.
Yeah.
You know.
All right.
So it's glued, showing up the other on it, so we'll.
No, it's okay.
It goes like this or it goes like this?
Like that.
I know. Hey, you guys printed it in the right direction. Let's wait one second for
Ready to go.
Dr. Fleming. I think he decided to run to the bathroom.
There you go, Dr. Hart, cowboy boots are on.
Very nice.
As soon as the presentation was over,
Oh, you should have worn them. You would have got a better grade. For the talk, style matters. What was that thing that you had in your P matrix? Coolness factor?
yeah, it looks cool.
It looks cool.
Yeah. There's a reason why I weighted the lowest. I wanted just one more thing and I wasn't sure what to put.
I mean, to be fair.
All
the
6
propeller does
weeks.
look- Yeah, like that.
I just recognized how close your guys' last names are with each other.
Yeah, yes.
Very good.
I thought there
Yeah,
was twins at
well,
first.
Yeah, that's us.
Yeah,
They
that's
look
not-
exactly alike. The glasses really do it.
Professor Patterson, with the wind tunnel, like, that actually throwing that in a real wind tunnel for us, because it's so long. Do you have any suggestions or to like? Yeah, we just do a shorter version, just almost 100% of your grade is going from
You
that.
got one.
Yeah, from that portion, so it will lose, you'd lose fidelities somewhat, but it's, I mean. Almost, like I said, almost all of it's gonna be just from that front portion. Did they already see it or?
No, they haven't yet.
Yeah, it won't be like 1-to-1, like you'll get pretty good original.
You can see.
You want me to fly?
That's creepy.
No, what?
The dimension was creepy. That's how you get the.
I was probably gonna be able to fly it slower.
I've seen plenty of things I'm ready to.
2:03. Let's get underway. Last talk of the day.
Push this into the ground.
Bring it home. 20 minutes of the talk. Then we have infinite time for Q&A.
For Garrett's,
I'm Dwayne Vicente and Damian Vincent.
and we are the 3D printed blended body aircraft design team. Over the course of this presentation, we're going to start with a brief introduction, go into some of the background research that we conducted this semester, go into the individual designs that we each came up with, our group design, and our moving forward steps, and leave some time for Q&A at that.
First of all, what is our project? So we were tasked to iteratively design and develop a 3D printed remote controlled blended wing aircraft. The project objectives are reaching 70 miles per hour and have a continuous operation time of 20 minutes, all while having a wingspan of less than half a meter in order to wind tunnel test in the physical wind tunnel here at MSOE. Current will be discussing the initial background research we did before designing our initial prototype.
So what is a blended wing aircraft? Blended wing aircrafts are known to be very aerodynamically efficient, way more efficient than the traditional tube and wing aircraft. The advanced design, where the body and wings are seamlessly merged, allows for the body to contribute to the lift along with the wings. Blended wing aircrafts are still mostly in experimental and prototyping stages, but they should be becoming a bigger part of the industry. So a aircraft in flight will have 4 forces acting on it: the lift, the weight, the drag, and the thrust. In order for the aircraft to gain elevation, the lift is going to have to counteract the weight. While in cruising, however, the lift should equal the weight. In order for the aircraft to accelerate, thrust must overcome the drag. When selecting motors next semester, we will be needing to look at this to make sure that we can reach the speed of 70 miles per hour.
With basic knowledge of the fundamental forces that play into flight, we research into different airfoils and what goes into airfoil designs. So all airfoils have characteristic parameters. The important ones being the chord line or chord length, which is used to measure the aerodynamic efficiency of the airfoil, along with the upper and lower camber surfaces, which are the external geometries of the airfoil, which affect the properties that ultimately dictate how efficient an airfoil is. There exists many types of airfoils, which if we were to dive into them, we would be here for like 2 days. But in a simplified version, there are many ways to generate airfoils. One common way, which is used in industry today, is the NNCA approach. Essentially, a set of parametric equations are used to generate points of a characteristic property. The type of equation that's used dictate what family or series that airfoil is categorized into. These airfoils are generated using that equation, and that equation generates the points along the upper and lower camber surfaces of the airfoils. While the group could go into researching and finding out the parametric equations used for all of the airfoils, there exists good resources that have that data readily available. Those are found in aerofoil.com and airfoiltools.com. And the group used those resources from the iteration phase to look for the group's design airfoil designs. Apart from the NACA method, there is the free-drawn approach to designing an airfoil. With this method, all of the geometric features of airfoils are designed by the user. Benefits of this is the airfoil is highly customizable, but a drawback is the design process can be tedious and not the CAD software used, because the constraints and the order in which you apply the constraints matter. So with the geometry portion of the airfoil covered, how does an airfoil work? Essentially, airfoils create a velocity gradients along the top and bottom surfaces, and those velocity gradients cause pressure gradients along the same surfaces. You would want high velocity moving air in the top to cause a lower pressure region at the top, and you would want lower velocity moving air at the bottom to cause high pressure regions at the bottom of the airfoils. This principle is dictated by Bernoulli, and the pressure difference it's what it generates. It's the main factor into generating lift.
So each group member did do their own research into existing patents related to blended wing aircrafts. Looking at these patents kind of helped us to start brainstorming ideas. These two patents helped us to kind of start thinking about the shape of our body, as well as how we're going to be placing our motors. This specific patent is for blended wing aircraft with embedded engines. We tried to, in our future designs, we were trying to minimize our drag with our motor placement.
So to start with, we need to test in virtual wind tunnels since we can't use the physical one right away. So we use the MSOE Rosie wind tunnel, which works by taking in whatever model we use and a Reynolds number to calculate the lift forces, drag forces, lateral forces, and a center of pressure, usually located roughly in the center of the object to avoid moments about the centroid. Tip it over and such.
So in order to get an understanding of what sort of lift force our goal should be to fly, we set up a basic force balance. So in order to stay in flight, we need the force of lift to be greater than the weight of the body. In order to get a rough estimate of our body weight, we did a very bare bones SolidWorks model and found that the density of PLA is about 1.25 grams per centimeter. and each of the motors should weigh about 58.5 grams. In total, we should be aiming for a lift of greater than about 20.8 newtons. So each group member was tasked with creating at least one individual design and presenting it to the rest of the team.
Starting with my design, I wanted to try to base it off of the YB-49 bomber plane. I used a free-drawn airfoil to design. My goals, I didn't really focus on the weight for this one. I focused more on trying to get a decently high lift to drag ratio, 1 at minimum, just for the sake of that. I wanted to try to make it relatively easy to 3D print with large body and long wings to make sure there's any room for internals. So here's the results. Here's the center of pressure. Not great with how far back it is, but here's the results of lift and drag with a lift of 14.6, drag of 8.2, and 8.02, excuse me, and a lift to drag ratio of 1.82. It's not great. It works. It has a higher lift than drag, but the weight versus lift doesn't quite work out the way it's intended.
This is at your 70 miles an hour?
Yes,
Okay.
A little bit less than that. But
just a touch.
okay. So for my design, I created my design with the goals of obviously to have a high lift to drag ratio, focusing on it being able to be easily 3D printed, and focusing on the design of the body to be wide enough to house the motors. So after doing extensive research through the airfoil database, I decided to use the Gattingen 387 airfoil, which was designed in the 20th century. It's ideal for low speed operations, like monoplanes, for instance. And it's a relatively simple design, so I thought that it'd be good for the 3D printing aspect of this. So these are the wind tunnel results from Rosie. I got a lift to drag ratio of 2.86, which is okay, not great. But the biggest takeaway from my design was the 39.8 newtons of force generated, which is much greater than our target goal.
So my design focused on producing the minimum lift of 20 newtons. Also, my design consisted of minimizing the drag by utilizing the loft features to smooth the surfaces and also provide a sufficient internal volume in the main body of the aircraft to house the electrical components such as the flight computer, the servos that will eventually control the control surfaces of the aircraft, and any other components that the team might decide to include in the aircraft. Using the model that was previously shown, uploading that to Rosie at a flight speed of about 70 miles per hour, the model produces a lift of about 24 newtons and a drag of 6.77 at an attack angle of 70 degrees. The attack angle of 70 degrees was chosen from an optimization process by intentionally uploading the same model, but at different attack angles to Rosie and choosing the highest lift to drag ratio from that set of models uploaded. One thing to note is that even though this model produces the highest lift to drag ratio, the lift force, while still being above the 20 newtons requirement that we established in the beginning, it's not the highest out of the three. And so this design consideration will be used when ultimately creating one main group design. After evaluating all of our designs based on a decision matrix, we culminated on this design. This design combines Earth's body to maximize the internal volume and the main body of the aircraft to house all the expected components like the servo motors for the full surfaces, the flight computer, and the batteries. It uses nine-airfoil geometry since it provided the highest lift to drag ratio, and it kept convenient, simpler aesthetic for easier 3D printing. These are the values that that Rosie calculated for the initial design, having a lift force of 42.8 newtons and a drag force of 9.2 newtons. The lift to drag ratio is about 4.65, and the center of pressure is slightly beside the center of the aircraft, but it's still in about that central. It's still in line with the core line of the aircraft.
So now that we have a finalized design, we decided to calculate our cruise velocity. First, we had to calculate a coefficient of lift using this equation, the force of lift from our Rosie results, the density and velocity of the free stream air, and the plan form area that we had to manually calculate. Taking that number, putting into this equation for the force of lift under cruise conditions, the force of lift is equal to the force of weight, which we calculated it to be 17.44 newtons. Subbing that into this equation yielded a cruise velocity of about 42.6 miles per hour. After doing these calculations, we did go back into Rosie and validate our calculations in Rosie.
All right, now that we have a validated model, now it's time to get ready to 3D print it. So to start with, I cut it in half since it's a symmetrical design. And then I cut each half into 4 parts: front of the body, back of the body, back of the wing, front of the wing. And then I also created pins and holes to connect all of them. And I also shelled out the body parts for any for internal mechanisms and such.
So I created a project plan in Microsoft Project that kind of details how we progress in our workload throughout the semester. Throughout the semester, Professor Patterson gave us various assignments to kind of keep us on pace. Those can be seen in red, and the intermediate tasks leading to those assignments can be seen in blue.
Moving forward, now that we have a printed design, we're ready to start physical wind tunnel testing next semester. Once we get that all settled, we can move on to.
Yes, so once wind tunnel testing is done, since this semester we solely focused on the aerodynamics portion of the aircraft, we will proceed to motor selection and placement, and also battery selection to ensure we select the appropriate battery size given our 20-minute minimum flight duration time. And we don't need a battery that goes necessarily over that time limit. Additionally, we will proceed to source for turbo to control the control surfaces. Since we focused solely on aerodynamics, we didn't take into consideration the control surfaces when evaluating the aerodynamic efficiency of the aircraft.
For our tentative budget, with just for preparation of next year, we just took the design groups last year for engine, transmitter, receiver, and batteries, just for reference for once we get to choosing next year. Once we get to choosing our own next year, we have these as reference, but we'll end up choosing our own come the time.
And these are a list of sources that we use for all of our background research as to know. Any questions?
Very cute group prep there. We did that in week 1 of the seminar. Very cute. Is it going to be a single prop, double prop?
So we plan on having 2 motors in the props, the number of props. We haven't narrowed down on that yet, but we will look into that next semester.
Because I think you quoted the weight of whatever it was, 20 something newtons. Is that just for the PLA?
No, that's the motor and the
Oh.
capacitor.
Okay, because that's, yeah, like 4.5 pounds or something, right? So that includes batteries and motors and.
Yeah.
everything for controlling control surfaces.
Yes.
So,
Should be good. Yes.
what about landing gear? Consider landing gear at all?
We looked at it, but the complexity of that is just not worth it. We prefer just.
Gonna belly it?
Yeah.
Yeah.
That's fine.
Pull it up, how are you gonna get it in the air?
Yeah, that's right.
I know last year's group kind of wants to do it, and I don't know if we'll have to do that, but that seems like a very easy solution. When it comes to testing, I'm sure we'll explore different variations.
Drop it from a 10-foot tower and cross your fingers.
Have you seen the tennis ball throwing tools for dogs?
Yeah.
Strongly recommend something like that
Okay.
because I've told you guys about someone getting caught in the face by one of the propellers. Like,
Yeah.
like he shouldn't. He has a scar. So, but also like it was wildly inconsistent from one person to another throwing it, and so something that would help anything like launching mechanism of whatever shape or size is probably going to help you get a little more consistent in getting it into the air.
That's good.
If you wanted to look into that, they have a lot of gliders that are launched with rubber bands. Those are gonna be longer than you'd want, but like your crossbow might be.
I don't know if MSOE will approve that as a line item, but yeah.
Dirty printer, right?
That was it from me.
I guess in terms of the electronics, have you considered space needed for those?
Space what?
Like the space needed for your battery?
Yeah, so like we have, it is hollowed out inside the like body, so I think there'll be enough space in there. If not, then we'll just have to increase it a little bit, but it is hollowed out, so it should be able to.
And the way the CAD model is set up, if we needed to increase the body size, the central body size, we could increase that because the transition from the main body and the wing itself, it's supposed to be the same geometry. So as long as the distance is scaled properly and the base of the airfoil is scaled properly, we shouldn't have that big of a problem with increasing the body size, increase internal volume.
Okay. Kind of a follow-up on that, did you look at all into like aircraft stability at all? Just because that is a much bigger challenge with the blended wing design. Say, traditional.
Yes.
I would say that's a lot of what we're gonna be doing next semester. This semester was primarily on the design of our airfoil and our body, making sure that we have the correct amount of lift to drag and, but we have a good understanding of what we're gonna need to be doing.
Another consideration, looks like you looked at single kind of airfoils. Did you ever consider varying the airfoil, I guess, down the length of the wing at all? Just because that's also fairly common.
Yes. So, and along my design process, I have, wait, could you?
There's.
So this design has 3 different airfoils along the wing. It has the base at the center line of the aircraft. It has another airfoil at this section and another one in this section. It turns out it's simpler to just have one airfoil geometry throughout the entire wing section because it simplifies the geometry and also.
Even if it's a 3D printed.
Yeah, if the airfoil geometry is very, I don't know if you can see.
Yeah.
It has some kind of grooves. Look at that. So. Yeah, I don't know if it. 1, 2. Yeah.
One thing too that I wanted to mention, because I know you're asking other people about being able to kind of quickly 3D print and exchange out broken pieces. Damien's done a great job of actually creating the pins. They weren't perfect our first time around printing this. We did have to glue some, but the ones that were working right, it was a very tight fit that I think should be able to be a good way to interchange broken parts.
Yeah, and since most, if not all of our components will be housed within the central body of the aircraft, it should be as simple as removing the entire wing section, putting the new one in, and should be good to fly.
think it'd be a tight fit for your components in there.
Yes.
By eye.
Yes.
I'd say for both teams, like think about how you want the wings to break away. Cause you want the fuselage to live, right? And that's what the group last year ended up doing better towards the end, is that they lost a motor and a speed controller because that fuselage took so much damage, but then they got better at having the other components break off without causing damage to the core. And so you might think about that, like you want it strong, right? But you also want it to break in a way where you can replace the fewest possible.
So did you look at any of the control surfaces that you need for this design?
Currently, we plan on essentially making these regions our control purposes. And have the servos extend from the main body and have some sort of shaft to control that. Those control surfaces.
Did you consider adding a vertical stabilizer in any of your designs?
So throughout the design process, we included this vertical toe section, which we planned on having as part of our stabilizer. But if we decide or conclude that we need to add a control surface in this region, we could modify this geometry to add a control surface, a vertical control surface.
Okay, that's the end of the day.
Pretty sense of time.
Happy holidays, everyone. Yay.